watching a plasma go up two brass rods vertically. That plasma, a conducting gas, an ionized gas, is being produced by a 9,000 volt alternating current source. That 9,000 volts is coming from the secondary of a transformer. The input is 120 volts, and yet we're getting 9,000 volts out. That's about a 75-to-1 ratio in voltage. We're going to find out how transformers do what they do. Now, before we do, though, I need to talk about safety a little bit. Now, almost all the things that we worked with in the earlier sessions were relatively safe. The worst thing that might have happened in most of them is that, like with the batteries that I had, they could put out a lot of current and something could overheat. You might burn your fingers. You might even start a small fire, but you'd be able to handle that. These devices that produce these high voltages, they're deadly. They're not toys. In 1 second, this device provides 1,000 times more electrons than those big spheres of a Van de Graaff generator at your favorite science museum. 1,000 times in 1 second. And in the next second, it does it again. So these devices can be very dangerous if the electricity flows through your heart or your brain. So please don't treat these as toys. Don't play with them. So let's get started with our exploration of how transformers are built, how they do what they do, and the kind of electricity that we need to make them work properly. And after that explanation of danger, I'm going to turn this off so nothing comes on accidentally. Now, let's take a look at this transformer right here. Transformers have three main parts. They have a primary coil. They have a secondary coil. The primary is where we put the power in. The secondary is where we take the power out. And the third part of the transformer is the magnetic field that links the two. The electrons that travel in this coil do not travel in this coil. They're electrically independent for all the transformers we will be talking about. There are specialty transformers that have the two coils interact, but for our purposes and all the transformers I've shown you for transmission and that type of thing, they are completely independent electrically, but they are coupled magnetically. And to get a real strong magnetic coupling, we use a steel core. Okay, that's what this E-shaped device here is. We use a steel core. I would complete the core by placing this on here. And now all of the magnetic field is pretty much in the steel core. Now you recall when we use a steel core, we multiply the magnetic effect of the coil by 100 to 1,000 times. And with transformers, we're closer to the 1,000. They're just special steels that maximize the magnetic field in the coil. Now, one thing about, let's operate this. And what we're going to do is we're going to power the primary with a 1.5 volt D cell, or two of them actually. So I've got 3 volts being fed into the primary, and then a secondary is going to be fed into this little motor here with the propeller on it. It's a basic commutator DC motor. And I'm just going to show you that I'm going to hook it up to a 9-volt battery. If I hook it up this way, it spins in that direction. If I reverse the polarity, it spins the other way. Okay, So we're going to be driving a DC motor, and our source is going to be 2 D cells. Now, when I turn the power on, what I want you to notice is which way the motor spins and which way this meter needle goes. This meter has a 0 right in the middle, so it could go plus or minus. When I turn it on, watch what happens. The needle moved that way and the propeller spun that way. It's on, but there's no power transfer. Let's turn it off and watch what the propeller and the needle do. The needle went negative, the propeller spun in the opposite direction. The power is off. Let's do it again. Turn it on, it spun that way, the needle moved to the plus, the power is on, but there's no power being transferred to the secondary or to the motor. Turn it off, and they go back in the other direction. Now I could put this switch on here to turn it on and off for me. Plus, minus, plus, minus, plus, minus, and the motor is spinning accordingly. Okay, let's take a look at what is happening. Why is that happening? Well, when we increase the magnetic field in the core, we generate a voltage in the wires out here in one direction. When we let the field collapse and go back to 0, we create a voltage in the other direction. That's why the motor goes one way and then the other way, one way and then the other way. Now we could fix that. We could use something called a diode. I want to introduce the diode to you. They're in a lot of your devices, in your power supplies, your battery chargers, and they look kind of like, I don't know if this is too easy to see, this little device here. They come in many shapes and sizes. Here's a bunch of them right here. Here's a tiny one. We're going to use several of these. Here's a larger one, and here's a group together, an array, and we are going to use that kind of thing too, an array. It won't look like that, but electrically it will be the same thing. Now, diodes come in sizes much tinier than that and much bigger than this one. Let's see how they work. Or I guess I should say what they do. So I've got this 9-volt battery, and you'll notice there's a yellow band on it. And I'm going to connect it to these Christmas tree lights with a diode in the circuit. When I hook it up this way, they light right up. But if I turn the battery around, nothing happens. Turn it back around, they light right up. Go this way, nothing happens. They only allow the electricity to go in one direction. They don't let it go the other way. So what we're going to do is we're going to insert these 4 diodes in a particular configuration into the circuit. They weren't in the circuit before, they were just sitting there. And let's put this back. And we're ready to go. So watch the motor. Notice the motor is spinning that way. It's hard to see when it's spinning. It's spinning that way, and all we're getting are positive pulses. Let's reverse the wires. And now we're just getting negative pulses, and the motor's turning that way. So the diodes convert a push-pull, push-pull, push-pull into either a push-push-push-push or a pull-pull-pull-pull. So the motor will spin in the same direction. Let's get back to the main event here, which is the transformer. Now, when we make transformers, we use we don't just use a solid block of steel. Let's get a little closer here with this, zoom in a little bit. So the problem is, if we use the solid block of steel, let me pull this back a little, the same effect that produces electricity in the copper wire out here will produce electricity in the core. So if it's a solid block of steel, the electricity will flow in the core. Well, that electricity is useless. It wastes power, and the core would get hot as well. But it wastes the energy. How can we avoid that? We laminate the core. It's made of layers and layers and layers of thin metal. So you can see that these are layered. And I'm going to show you, this is from another little smaller transformer, that little E-shaped that you have here. And I'm going to spread these, and you can see that it's laminated with these layers and layers of thin strips of steel, and they have some kind of an insulating material, just a coating, so that the electricity doesn't flow across the layers. And that cuts down on the electrical currents in the core drastically. So it really makes transformers a lot more efficient. Now, if you're having a little trouble understanding or accepting that the changing magnetic field in here is producing electrical currents without anything moving, let's review something we used a while ago in one of the earlier sessions. I think you might remember this. So we've got a coil of wire, and it's connected to this little motor with a paddle on it, and these lights as well. What I'm going to do is I'm going to take this pair of magnets, U-shaped magnets, and as I plunge them into the coil, watch what the motor does. If I move it fast enough, I could even get the lights to light up. So what we're doing is we're changing the magnetic field in the coil. Only with the transformer, instead of plunging a magnet in there, we're just changing the magnetic field by turning this coil on and off. Okay. Well, why go to the trouble to do that? What do we get out of this? Well, let's take a look at a diagram, and that will help us. So here is a typical transformer. Now, it's shaped differently than the ones I was showing you. They have kind of an E with a top bar on it, whereas this is more like a loop, but it doesn't matter. This is just as good a transformer. I drew it this way because it's easier to see. It's easier to explain what's going on. But look at the three main parts. We have in gray, we have the core that links the two coils, and then we have this coil, or in this case that's the primary, that's the secondary. This is a step-up transformer. Step-up refers to what's happening to the voltage. If the voltage is going up, we consider that a step-up transformer. If it's going down, we call it a step-down transformer. So this is the primary, where the power comes in. This one here is a secondary, where the power is taken out. Now, let's look at some patterns here. We've got 20 turns of wire on this side, on the primary, but over here we have 120 turns on the secondary. Now, the amount of magnetic field is the same for both coils because this magnetic material is so good it carries all of the magnetism. There's hardly anything that's going through the air. So since it's the same, when it changes, it produces a voltage in each of these coils, and the amount of voltage that's generated is proportional to the number of turns. And since over here I have 6 times the turns that I have over here, I produce 6 times the voltage. So I'm putting in 200 volts across this coil, I'm getting out 6 times that, or 1200 volts across here. Now when I start drawing current out of this coil, in this case 10 amps, I need to put in 60 amps on this side because of conservation of energy. So 1200 volts times 10 amps is 12,000 watts. 200 times 60 amps is 12,000 watts. I get out what I put in. Now that's if I have a perfect transformer. Well, we never have perfect machines, but some of the big ones that the utilities use come awfully close to it. Some of their big transformers are like 99% efficient, which is like you're getting out almost everything that you put in. Let's take a look at a step-down transformer. Looks the same, doesn't it? Well, it is. It's the same drawing, except we are putting the power in on this side. We're taking it out on this side. So the ratios are the same, 120 turns to 20. That's a 6-to-1. If I apply 1200 volts across here, I will only get 200 here. However, if I draw 60 amps through this coil, I only have to provide 10 on this coil. Again, 12,000 watts in, 12,000 watts out. Let's take a look at a couple of transformers that you can compare the thickness of the wires and the windings. And we'll zoom in a little so you can actually see the individual wires. Okay, I think you can see the individual wires in the secondary there, the one that's the thin wires, lots of turns. There's about a 20-to-1 ratio in the number of turns. There's 20 times more turns here than here. And this wire is a lot thicker than that wire. So higher voltage, fewer amps, thin wire, lots of turns. Over here, thicker wire, higher amperage, lower voltage, fewer turns. Let's look at one more. This is one of the transformers we used on our transmission session. And it's about a 10-to-1 ratio. And you can see that the high voltage side here, this is the high voltage side here, has lots of turns, thin wire. The low voltage side, high amperage, has thicker wire, fewer turns. It's pretty typical of what you find inside of a transformer. If you're still kind of wondering about this whole idea of trading volts for amps, like, wait a minute, what's going on here? Well, you know, we do that kind of trading in our everyday lives, like with mechanical systems. So let's take a look at some examples. Let's take this cordless drill here. Okay, you can see the little gear is turning very fast, turning the big red gear, reducing the speed but increasing the torque, and then the little blue gear is connected directly to the big red gear, and the little blue gear is turning the larger blue gear, again increasing the torque and reducing the speed. So we're able to do useful work with the chuck, even though the motor is spinning very fast and doesn't really have much rotating force, or what we call torque. One more example. Let's say I want to pull this nail out here, okay? And it takes about 200 pounds. Well, I'm not strong enough to do that even with two hands. I'm not going to be able to pull with 200 pounds. So what I'm going to do is I'm going to get a simple machine called the lever, and specifically in the form of a crowbar. Now, this crowbar has a 7-to-1 advantage for me. There's 2 inches from the fulcrum here, 14 inches to the fulcrum here. And if I push on here with 30 pounds, I can exert 210 pounds on the nail and remove it. It's great. It's all I needed. I'm happy. End of story. However, if I'm doing engineering work and I'm going to make a machine that's going to be removing those nails, and I've got to motorize this, then I got to think about, what am I trading? I'm not getting 210 pounds for free. I'm not suddenly converting 30 pounds into 210 for free. I'm trading something. What I'm trading is, in order to move this nail 1 inch, I have to move the crowbar 7 inches at this end. 7 times 30 is 210. 1 times 210 is 210. That's what I've got to do. I've got to trade distance for force. And that's what the transformer does for us. We trade amps for volts, volts for amps, depending on what we need to do. And you recall, to send electricity long distances, we wanted high voltage, low amps. That's how we get our power. Now, when we started talking about transformers, you saw that I had to keep changing the power to the primary in order to get something out of the secondary. And I did it with a mechanical switch. That's really not the greatest way to operate a transformer. Now, we do have electronic switches, digital switches, that we use to do that under certain circumstances. But our power grid doesn't do that. Our power grid starts out with a kind of electricity that's constantly changing. We call that alternating current. And I want to graph that for you on this machine here, on this oscilloscope. But before I graph alternating current, I would like to show you what direct current looks like. Okay, now we're going to graph time and voltage up and down. Time in this direction, voltage up and down. So let's take a look at what 9 volts, and we'll do negative, a negative 9 volts. Let's get a close-up here. So here is negative 9 volts. The blue line right now represents the 0. The yellow is 9 volts negative. Let's switch those around. And then this is 9 volts positive. Notice how steady and continuous that is. That's time, and it's not changing. That's what we call direct current. Not very descriptive. A better name would have been constant voltage, constant current, steady current. But we call that direct current. Now, let's take a look at what alternating current looks like. This is the kind of electricity that you get coming out of the wall of your house, out of the outlets. Notice how it smoothly goes from negative to positive, passing through the 0. There's the 0 right in the middle, okay? Now, when we specify the voltage of alternating current, we don't specify it based on the peak. We specify it on a special average. We use 70%. Turns out to be 70% of the voltage from 0 to the peak. Like your 120 volts coming out of your outlet at home has a 0 to peak voltage of about 170. I'll take this off again so you can see where the 0, whoops, I forgot I had adjusted the voltage to show you the 70%. Remember, this is time, it's not position. So I really want to make it clear that if I've got a wire, the electrons are not doing this. They're going back and forth in the wire. Now let's pretend like these are giant electrons, okay, in a wire. Now, obviously, if it was in a real wire, it would be full of electrons, and I would have a circuit. I don't have a circuit, so I had to leave a space in some of the tubes so we can move the large electrons. Now, in direct current, the electrons are always going in the same direction unless we switch the terminals of the battery or the generator, and there they would go in the other direction. Switch the terminals, they go in that direction. Alternating current, they're doing this all the time, back and forth, 60 times a second. Now, you may recall from an earlier session that we found electrons travel very slowly on the wires. There's so many available, they really don't have to travel very fast to give us the amperage we need. So what happens with alternating current is these electrons are sitting in the wire and they're pretty much vibrating. I mean, 60 times a second is pretty fast. And so they're just sitting there in the same position going back and forth from here all the way to the power plant with some transformers in between. So the electrons aren't coming from the power plant with alternating current. With alternating current, they're just, what's coming is the vibration. The vibration is occurring at the generator, at the dam, or at the nuclear plant, or at the wind turbine. That vibration is being sent down the wire, and we're picking it up here as energy. So I hope you've enjoyed this session, and I'll see you next time.